All right, thank you, Harold. That was a great introduction to what we're doing and at SMRU Consulting. And thanks also for the introduction to the detection functions. If you haven't heard about those, I'm going to talk about them a little bit today. For some of you poor folks, you've sat through part of this presentation before. So if you're one of those, feel free to take a nap for the next 10 minutes. And then for everyone else, yeah, I'm going to talk a little bit about our most recent hardware. The Coastal Acoustic Buoy for offshore wind. I'd first like to acknowledge my co-authors. Of course, this is what happens when you get a whole bunch of people that don't like their picture taken. So our funding was initially through the U.S. Department of Energy and University of Maryland. DFO has supported our transition to looking at killer whales as well. So the Cabal was originally developed for monitoring exclusion zones off the US East Coast for offshore wind. In the US, they said you need to monitor 10 kilometers for North Atlantic right whales. So these are a baleen whale that produce low frequency sounds below a kilohertz. There's a couple different ways you can do it. As Harold indicated, we're looking to use bearings to tell whether or not a call came from inside a stated exclusion zone or outside an stated exclusion zone. This obviously has other applications when it comes to killer whales, which I'll talk about in a bit. So what is the Cabal? It's a cab, which Harold mentioned. This is a surface expression buoy. When it's a drifting cab, we have our hydrophones just dangling down at the top. We can connect radio, cell, or Iridium satellite, and it can send data back to a base station nearby. Or what we're developing now is a cloud-based storage system, which anybody can theoretically access at any point. For this iteration, instead of having an anchor down to the bottom, we have a data cable. And then we have on the bottom a lander, which has our 3 hydrophones, which give us bearing, as well as our batteries and our onboard processor and recording equipment. So Cabals can relay data both in real time, as well as record all of our data. So Harold nicely talked about, whoops, skip one. Okay, so this is the other really cool thing about the Cabal. We have a 2-stage processor. We've got a low power Decimus recording system on board that has PAMGuard running, or a version of PAMGuard running that's looking for right whale upcalls. Right whales are very easy. They make a bunch of sounds, but for the most part, they make these upcalls, which are contact calls, and they're pretty stereotypical. And there's a predictably not great detector within PAMGuard for these. So we can run that and send our upcall clips back to either the database, which Harold showed a little bit, which is online, or to someone who's monitoring it actively. And then as a second stage, we have a neural net processor running on a local computer. And this is our precision and recall. So what proportion of calls did we detect versus what is our false positive rate, more or less? And this is what the field was in probably 10 years ago. And then this is the neural net detector as of late. An ideal detector, our precision and recall will be in the upper left corner. Okay, so this is what it looks like when it's running in real time. We've got a user who's looking at spectrograms coming in, just making sure all of our systems are working. It will send detections back and a little clip around each detection. And then you've got another graphic user interface that is showing you the bearings as they arrive. It's not showing them right there, but I promise you it does. And then you can't quite see it. That's our second stage neural net detector. So that first stage PAMGuard detector, it catches a lot of stuff that's not actually an upcall. And our neural net really cuts it down a lot. So last year we went out and similar to what Harold did, we tested this on the East Coast of the United States. We deployed 5 of these things And then we played back simulated up calls in the area. Is this a video? I think this might be a video. Oh yeah. So this is what it looks like deploying a cabal system from the short-lived drone. I didn't crash the drone, you crashed the drone. Yep, so it's a relatively small system, but it still does require a boat to deploy it and a winch. Okay, that's enough of that. And just like Harold played back simulated tones to the detectors that you're working with, we also played back simulated tones. And these are very right whale-like calls. So one of the things with any hardware, how reliable is it? And here's our system uptime. So did the systems go down as a function of time over our 38 days? Excuse me, that was not right at all. 42 hours, at least on the East Coast that we tried this. Just moving the chat here. So across 42 hours, the data buoys were sending data between 70 and 99% of the time. This one down at the bottom, we actually think it lost radio communications. Oops, next please.
What are the gaps there?
That's when it wasn't, those are the downtimes. So this one behaved the best, and some of the others, actually this one wasn't in the water, that was the one, two, yeah. Oh, that's full system. Oh, okay, so that's all 5 together that we had data. So again, this is how far can these things detect right whales? But this isn't actually looking at right whales, it's how far can it detect our radio system. So this is the percentage, ooh, RSSI. Actually, this is a SAM question. But this basically talks about how far we can get away with a radio system on the cab as opposed to iridium or cell tower. Detection functions, these are my favorite things ever. Harold talked about detection functions for killer whales, and it's dependent on the ambient sound level and also how loud the call is. Another way to think about that is what is the difference between the source level of the call and the ambient noise level as a function of range. So that's what this is. So as a function of range, we have the portion of calls detected as a function of signal excess. If you want to think about this as ambient noise going up on the y-axis or source level descending on the x-axis or y-axis. So here you can see at a far distance, the call needs to be either very loud or it needs to be very quiet. And you might also notice this is G not what we expected. That killed at the DCLDE. So G naught is our probability of detecting something that's right on top of the hydrophone. So we found that there was a slight issue, and long story short, we fixed it. Right. So bearing estimation, like this whole thing is about bearing estimation, and we need to understand how good our bearing is. So in the case of the right whale up calls, this is our distribution of bearing error in degrees. You have to zoom in to see where it is. And we did really, really well. Most of our error was in plus or minus 10 degrees. Actually, I think it was 2 degrees with our standard deviation. We don't quite trust that. I think we were biased a little bit. And now, now we have our detection function as a function of signal excess and our bearing error. So we can start looking at questions regarding our exclusion zones, or how far are we detecting things? How accurately are we detecting things? So this is just a little simulation of a cabal system on an exclusion zone. The purple is the exclusion zone, and green is calls that would have triggered a false alarm, like, oh no, you have to shut down or stop work or whatnot. And this is a system without bearing. So everything outside of the exclusion zone that it detected, so this is the equivalent of a single sensor hydrophone, would have caused a false shutdown, and then all of the yellow is correct. So it was the correct conservation action. When you pop in the bearing estimation, you do a lot better. You still get some false shutdowns, which we are totally okay with. This is conservation for right whales or killer whales, but it gets a lot better. Okay, now the astute among you may have noticed I've been talking about right whales, not killer whales. So of late, we actually have been rejiggering the system to monitor killer whales and ask the same questions about killer whales. One of the cool things about PAMGuard is that it's open source, but also those detectors are available for right whales and for killer whales. We don't currently have a really nice neural network integrated for right whales, but we are working on that. So here's a map of some of our deployments of the Cabal system with respect to monitoring killer whales. As Harold noted, we have a system out at Carmina Point. We also had one down in Seattle and then Point Roberts. The one in San Juan Island is a test system, which I have lovingly called Cabal on a stick because it is cabled to the lighthouse station, so we don't have to pull it up every time and service it. Unfortunately, it only has one hydrophone, so we can't test bearing. The one at Carmina Point, because it's a bit more remote, we don't want to have to go out and service it, so we doubled the battery capacity. And yeah, Harold showed this slide a little bit. I want to correct you just on one thing. So what this is showing, this is a screenshot of our cloud-based system that's showing the number of PAMGuard detections in 20-minute bins. A PAMGuard detection is not a killer whale detection. Again, PAMGuard is great. It's awesome. If you work with it, you know it's a little finicky. And the detector is, again, predictably, yeah, it's got a high false positive rate.
That's why we have Lucy to look at.
Yeah. So, but the other great thing about this is you say, okay, I want to download the 20 minutes with the highest number of detections to see if those are killer whales. Oops. And that's what we've got here is you can click on that, download it, listen to the sound, look at it. It's an MP3, so it's pretty compressed. And this is what we're doing to move with killer whales. And then that bearing stuff. And I think this has real applications to Bruce's work with predictive modeling, is what are the animals doing around these hydrophones? So this is a polar plot of some bearing estimates as a function of time. So on the up, this is one encounter on the upper left. So you can see in this case, it goes, reads just like normal text. So you go, the animals are largely staying around 135 degrees. They're not moving too much over the period of time. And then the polar plots on the right, that is more indicative of animals moving by the sensor as they appear to be traveling. So that's really interesting work that we can do. Of course, we haven't validated this as well as we have for the right whales. Again, right whales are kind of like cheating. The calls are in a very narrow band, or the calls that we're targeting are in a very narrow band. You don't often get right whales calling and counter calling and pods spread out across a kilometer or more. So these are things that we really need to start to get a handle on. That's basically my summary. So we've got the Cabal. It was originally designed for offshore wind, but it has real practical applications for monitoring killer whales. We added some batteries to make it last longer, and we're currently evaluating its performance for killer whales in a much more complex habitat with much more complex animals. Don't tell right whales I said that. Mouth this big, brain this big. And then, yeah, we've got a very cool website that we're working on with the user interface that should allow folks to download data, or at least MP3 versions of our data, and show detection history. And the thing that I'm very excited about is right now our neural net detector, even for the right whales, these things are really big. Just the size of the files and the processing power to run them. We can't have it running on the Cabal yet, but we're upgrading our technology within the Cabal such that we could have those neural nets on board. And yeah, that's about it. It's fairly quick. So yeah, any questions?